I'm Emily Mower, Provost, and I'm an assistant professor here in the computer science department. And so what I'm going to talk about today is how we can use emotional noise to better understand how people actually perceive emotions, or really more fundamentally, how we can use engineering tools to gain insight into human behavior. And one of the really exciting things right now is we see this explosion of interactive technology, either looking at avatars that are designed to teach people something ranging from emotion to any number of other activities. We see robots that are designed to help people recovering from strokes or in various other rehabilitation contexts. We have personal robots that are just designed to be cute and to be fuzzy. But what's really interesting and what's really important is that research has demonstrated time and time again that if we want people to be able to actually adopt this technology in the long term, then we fundamentally need to understand their behavior, we need to understand their needs, and we need to understand what their state is actually telling us, what their behavior is actually telling us about their internal state. But even more fundamentally, the reason this is so exciting is we have this amazing opportunity to start collaborating with a lot of the sciences, looking at how we can start trying to figure out more about human behavior by using engineering tools. We start to see overlap in research in children with autism, or looking at individuals with depression. We see overlap with marital therapy, general interaction dynamics, psychiatric disorders. And really, the hallmark of a lot of these conditions are disordered emotion production or disordered emotion perception. So fundamentally, any kind of insight we get from an engineering perspective about how emotion is produced and how emotion is perceived is going to directly lead into additional streams of information that clinicians can use when they're diagnosing individuals with these disorders. Now, all of this sits within the general umbrella of social signal processing. Now, social signal processing looks at a human and some sort of an interaction partner. And what we'd like to try to figure out is how we can go from what this human is expressing to figure out what this human needs to know, or maybe even alternatively what this human needs to know about what these people are expressing. And it has a series of steps. We have feature extraction, where we're trying to figure out which modality, the voice, the face, the body gestures, contribute information that we care about. We then have to quantify this information using feature analysis and processing. And then comes the tricky bits. We have to figure out how we actually want to quantify the type of data that we've recorded. Now, the reason this is hard, the reason this is sort of an interesting machine learning question, is that the types of targets that we go for directly depend on either the interaction partners that we care about or possibly even the human, him or herself. And so we see this really fascinating feedback loop between human behavior, human needs, situational needs, and the needs of the other interaction partner. Now, this is a giant field, and clearly in 20 minutes it's probably not the right time frame to actually go over everything. And so we're going to focus on just a small part today that's looking at feature analysis and processing and further quantitative data modeling. Now, all of this is going to sit within the field of emotion. And so the first thing that we need to talk about is how we actually would quantify it. Without the quantification of emotion, it's hard to talk about how we would actually use this in an engineering context. Now, luckily, there are two great descriptions for emotion that we can borrow from the psychological community. There's a continuous framework which describes emotion in terms of property, with this idea that emotion can be defined in terms of dimensions. So, for example, how positive versus how negative is it? How calm versus how excited is it? Really just expressing emotion not in terms of artificial labels, but in terms of the properties it inherently possesses. Now, alternatively, there's a discrete framework that says, OK, basic emotions exist. They exist across higher primates. There's fMRI evidence that for centralized regions in the brain that deal with these types of processing. So there are discrete categories. Common ones include things like anger, happiness, sadness, fear. These are kind of generally well agreed upon basic emotions. Now, the type of definition is not an agreed on question. There are some communities who strongly believe in the continuous framework. There are some who strongly believe in the dimensional framework. And we try not to get into that argument. We merely say it's possible to map between these two frameworks, and we happily use both of them. And so the great thing about it is that, let's say we consider valence. This is positive versus negative, and activation, which is calm versus excited. The interesting thing is we can map these semantic categories onto these dimensional plane. And so, for example, happiness can be described as positively valenced and very excited, where something like anger is negatively valenced and still very excited. Something like sadness will be negatively valenced and more calm, and neutral tends to be a little bit southwest of the origin. And so really what this gives us is a way of going from perceptual judgment to some sort of numerical representation we can use when we process this data. But before we even get there, the question that we have to ask is, how are we going to label this data? And we say, OK, no problem. From an engineering perspective, we've got this solved. We've got some sort of audiovisual data. We do some kind of human evaluation, and we get some kind of labeled data. And we go from here. But the problem is that we still fundamentally don't really understand what that process is. And so the goal of this work, this work is a sort of our new foray into this area of looking at sort of emotional noise to understand emotional perception. But the whole purpose of this area is it's going to allow us to better understand what's going on in this black box of human evaluation so that we'll have a better understanding for what typical emotion perception actually is, and even more fundamentally, how we can lead to this next generation of knowledge-driven algorithms for emotion processing. But what's the problem? So there's a current limitation, and that current limitation is that we have fundamental correlation between the information that's presented in our voice and the information that's presented in our face. They're produced by the same underlying process. And so the issue there is that when we're looking at both audio and visual features, or audio and visual cues, we have this fundamental correlation. It's very, very difficult to understand causation because the two sources of information are correlated. And so what we'd like to try to do is figure out which of these features across the face and the voice are actually contributing to perception. Or more fundamentally, we'd like to sort of tease apart this cross-modal feature interaction to really get insight into audio-visual emotion perception. We'd love to be able to come up with quantitative models that say, given that my voice has this level of pitch and this level of energy, has these frequencies, and my eyebrows are doing this, my mouth is doing this, I can say that I'm angry. Because once we understand that, once we understand how people are jointly using audio and visual information, we can start to approach these various mental health conditions, for example, autism, which doesn't have equal processing across the face and the voice. But the question is how we're going to do this. So the way we're going to do this is actually borrowed from this amazing phenomenon called the McGurk Effect. And so are people familiar with this? Is anyone familiar with this? I'm very glad I have a video then. OK, so what I want everyone to do for 1 second is just watch this video. Actually, no, we're going to listen first, but don't watch this video. Just listen to it. And tell me what you hear.
Ba, 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 ba.
People hear that?
Ba, ba.
Anyways, he said ba, 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 ba. So now you're going to watch this, and you'll see, oh, nothing. You'll watch this and see you see ga, hopefully, ga, 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 which is the movement associated with the lips. Now, I'm not going to play them together because clearly no one's going to be able to hear this. But what's really interesting is that when you actually have this combination of the sound ba with the lip movement associated with ga, the perception is actually the sound da. And so I very much recommend that people Google the McGurk effect and look for the guy with the long hair, because it's a really, really, really interesting perceptual phenomenon. And so this motivated a lot of research in the emotion community, trying to figure out if what we see with phonemes we can actually also see with emotion. And now, it's not really clear that an angry voice plus a happy face is going to equal sadness. There's no logical reason that that would be something we would expect. But what's really interesting is that what we can do is try to understand how the information in the voice and the face are differentially weighted when people are observing these emotional clips. And we can use this to better understand how audio and video bias perception, and even more fundamentally, the different audio and video features that are contributing to perception. And so what we want to do is recast the evaluation problem. So for example, these are clearly not the stimuli we're going to be using, in that these are not humans. But let's say we have an example text that says a third volume remains to be published. Now, it's important when we're creating these stimuli that we have the same lexical content across both channels. If it's different lexical content, it's going to be very hard to create the illusion of synchrony when the lip movements are very drastically different. But what we want to do is we would like to pull out the audio and the visual information from, for example, a happy clip, pull out the audio and the visual information from the angry clip, somehow align these two things to come up with a new clip that's composed of, for example, a happy video and an angry audio. Because then we can, again, really start to ask about how people are using this information when they're evaluating emotion. And so we're going to work with this pipeline for the rest of the talk. We're going to talk about first how we generate and evaluate this data, how we can then understand the perception that results from this data, and how we can estimate perception using the information that we have in our clips. So first, the generation. So the way we actually create these, I'd be happy to talk offline about this. It turns out it's actually fairly complicated to create these, which is why, until this work, they did not exist. So an actress records sets of different emotions over different sentences. So for example, a third volume remains to be published would be recorded in anger, in happiness, in sadness, and in neutrality. Then what we do is we break out the video stream and the audio stream, and we use the audio stream to force align to two different transcripts. So now all of a sudden we have the timing from the audio information, we have the timing from the anger, and we have the timing from the happiness. And so what we want to try to do is figure out how to align these two transcripts such that we'll have information about how the accompanying video will need to be warped to resynchronize with the audio. And so we do the forced alignment using a tool called sail align, and then we're going to iteratively drop and add frames from the video to create now video that's synchronized with the audio of an opposite emotion. And so what you end up having is a new clip that's composed of, for example, in this case, a neutral voice combined with a happy face. And so I'm going to hope people will really strain their ears to hear this one.
A third volume remains to be published.
Can people hear that at all? OK, fantastic. She's very loud when she's angry. So a third volume remains to be published in an angry voice. And so what we're going to do now is look at two different clips composed of two different types of audio streams. So for example,
a third volume remains to be published.
So it's the same exact video, but now with happy audio. And
a third volume remains to be published.
Now the same thing with neutral video. And so now we get to ask how perception changes as a function of this new information. And to do that, we need to introduce definitions. So for example, we're going to refer to the original clips as original audio-visual. These were the angry voice, angry face, happy voice, happy face clips, the things that you might actually see in nature. We're going to call the other ones reconstructed audio-visual information. Now these occur when you have this mismatch. So for example, a neutral face and a happy voice, or as we saw, an angry face and a happy voice, this reconstructed information. Now to create these, we have sets of clips. We have 18 sentences that are repeated across 4 emotions. So that gives us an original set of 72 utterances, 72 audio-only utterances, and 72 video-only utterances. We're also going to have these reconstructed audio-visual. And so for each of these 18 sentences, we have 12 new sentences that are the permutations of the 4 emotions. So for example, angry, happy, angry, sad, angry, neutral, et cetera, down the line. So we're going to have 216 of these reconstructed clips for a total of 432. We do a mechanical Turk study with 117 evaluators. This will allow us to, we'll ask people to observe the audio only, the video only, the audio visual from both the original and the reconstructed to understand what kind of perception we can get. The only restriction we made was that the people had to be in the US. It was our attempt to try to constrain cultural differences in perception. We paid everyone 10 cents, which ends up working out to about minimum wage. And we filter using weighted kappa to remove our worst evaluators. We also asked people to label the discrete emotion, angry, happy, sad, and neutral, the valence, which was positive versus negative, and the activation, which was calm versus excited. And so once we have this data, we can really start to ask about not only perception, but perception change, which will lead to 3 questions. So the first question I'm going to just handle very, very briefly in a second to focus on the second 2. The first question asks if this multimodal information, the audio and visual information, differs in the perceptual effect from either the video-only information or the audio-only information. The second question we'll ask, given the information that's presented in the audio-visual clips, can we try to estimate perception? Can we decide where in this valence activation space this new clip will sit? And the last question is slightly more complicated. In the last question, we're going to take these reconstructed audio-visual clips and really try to understand the impact of the modality that changes. And so let's say we had two original clips. We had a neutral clip and we had a happy clip. And what we wanted to create was this new clip that was composed of a neutral face and a happy voice. Well, interestingly, the only thing that actually changes from the neutral audio-visual clip is just the audio information. And so now all of a sudden we can explicitly ask, what is the effect in changing a single modality on dimensional perception? And so we're going to be trying to estimate perception change as a function of unimodal feature change. But first, looking at perception, just to get a sense for, again, where in this valence activation space these clips actually lie. So if we look over right in the center, this is the perception in the valence activation space for these original clips. We can see that happiness is generally in the positively valenced high activation space. Anger, the red, is in the negatively valenced high activation space. And we see quite a lot of perceptual overlap between neutrality and sadness, which is very, very common. Now, what's kind of interesting is that if we look at the unimodal cases, so looking at only audio evaluation or only video evaluation, we can see that there's much more valence differentiation in video than in audio. Now, what I would argue is much more interesting, though, is looking at what happens with these reconstructed audio-visual clips, these clips that have conflicting emotional information. And so if we look at these happiness, for example, happiness, we're going to fix the information expressed on the audio channel. So for example, the blue is now happy video, happy audio. The red is angry video, happy audio. The green is neutral video, happy audio, and the black is sad video, happy audio. What we can see is that the perception of all of these things immediately shifts kind of towards the angry quadrant, but not nearly as strongly as it does when the video is fixed and merely the audio is changing. And so that leads us to a set of two hypotheses. One which going to immediately discount, which is that there's no difference, except for in very small number of cases, there's almost no difference between the original audio-visual multimodal presentation and either of the unimodal presentations. But what we see in general is that these reconstructed audio-visual clips have a strong perceptual difference. In general, the valence is statistically significantly different in perception, looking at the multimodal versus unimodal in all cases. And in terms of activation, the level of excitement, it's different in almost all cases, which I could cover afterwards if people are interested. And so now what we want to try to do is estimate this. We know there's a difference, but now it's important to estimate what that might be. And to do this, we're going to use a suite of audio-visual features, which to some extent I'm going to gloss over in that I was just told I have 5 more minutes to wrap up. But generally, we're looking at features that encompass the entire sentence. So we're looking at statistics over the entire sentence and trying to estimate how these statistics will tell us about the perception that people are making. The video is extracted at the frame level using the toolkit called Borman. And rather than using the individual points in the face, we're using distances between points, which is common in one of the facial animation parameter frameworks. And so just as a reminder, what we're trying to do is estimate perception given the audio-visual information in the clips. And we're trying to estimate the valence information and the activation information. We do this doing linear regression, removing or entering terms when they have a p-value that's greater than, is less than 0.05, and removing them when their p-value is greater than 0.1. And we're going to look at r² to get a sense for how well we can actually do this estimate. So in general, we find that for the original audio-visual information, the audio cues provide a lot of information about activation and some information, although less strong information about valence, whereas the video is actually providing both. Now, if you reflect back to that graph that we saw earlier, we saw that in the original audio-visual case, the video presentation was actually quite similar to that audio-visual presentation, but the valence differentiation for that audio plot was actually quite a bit less. So this supports the graphical findings. For this reconstructed audio-visual, what's kind of interesting is that what we're trying to do is just estimate perception, not perception change here, just perception. And what we find is that we can do it to some extent when we're looking at activation. And we cannot do it at all with respect to valence. The audio cues seem to be providing us with almost no information about how this reconstructed audio-visual thing is being perceived. Similarly, in the video, we see that the valence is being provided by the video cues, but almost no activation information. And what's kind of interesting is that from a classification perspective, one of the things that you realize very early on when you're doing multimodal classification is that audio is great for activation, video is great for valence. And so what's kind of interesting is that these findings actually support the fact that this sort of differential perception is actually occurring. But what's really interesting is that there is evidence for multimodal perception. Maybe audio alone cannot predict perception. Maybe video alone cannot predict perception. But unified, they are providing information. And this becomes important in question 3, because in question 3, what we were trying to ask is, can we estimate perception change using feature change? And so as a reminder, the only thing that's going to be different between one of the original audiovisual clips and these new reconstructed things is a single modality. And so what we'd like to know is if we can actually predict how perception changes as a function of the feature level change. This tells us that people aren't doing things randomly, that there actually is method behind the way people are integrating audiovisual information. And so we're going to do the same type of model that we did previously, which I'm going to kind of gloss over for time, and say that in general, what we find is that perception change can be explained by both modalities, which is important. Because if you remember, what we saw 2 slides ago was that audio provided almost no valence information, audio provided almost no valence information, video provided almost no activation information, but the change in their modality, the change in that feature level information going from the original audiovisual to this reconstructed audiovisual is allowing us to understand how the reported perception is going to change, which is really suggesting that when it comes to integrating audio and visual information, there's a set way that people are doing it. They're not just doing it randomly. They're not just ignoring information. They are, in fact, integrating both parts. And so what this allows us to do is understand features. So cool. So I'm out of time. So it allows us to understand features. That is just fantastic. Audio and video, even better. And really what we find is that audio and video, they're both providing perceptual information. People are integrating this information in a very set way. And it's really exciting because what it means, what we're actually moving towards doing now is trying to understand how individuals with disordered emotion perception, for example, individuals with depression or bipolar disorder, are differentially processing this type of information. Can we understand where the deficits in emotion perception actually are? This fits within a broader umbrella of looking at both emotion perception and emotion production, which is something that my lab is focusing on. And with that, I shall say thank you and break for presumably 1 second of questions. So thank you, and thank you for getting here early. Much appreciated.